Hello, I am Ahmad, and in this video I am going to talk about essential boundary conditions, neutral boundary conditions, and equilibrium boundary conditions. To solve an element for the stability, we need to find out the governing equations. So in this case, we might need boundary conditions and also the equilibrium boundary conditions. In this video, we will see how to define these. Let's see. Let's assume we have one element with the length of L and at point A and point B, we have certain conditions in terms of rotation and displacement. At point A, we have the rotation at point A. Point B, we have rotation at point B. It can be 0, it can be something else. At point A, we have deformation at point A, and at point B also we have deformation at point B. Let's assume from left to right the orientation and downward V representing the deformation and at each point. According to the other video that we recorded, we know that total potential energy of a beam, elastic beam, is calculated according to equation of half 0 to L EI kappa power by 2 dx minus E divided by 2 integration from 0 to L V prime power by 2 dx. And P is the actual force in compression. And also, we determined kappa can be written as minus second derivative of V divided by square root of 1 minus V prime square. When we are looking for the bifurcation point or the buckling force, we are not talking about the post-buckling. As a result, in that sense, if we can recall from the other video that kappa can be written as a second derivative of V times 1 plus 1 over 2 V prime square. This is useful when we are looking for the post-buckling analysis, but when we are looking for bifurcation point, so we can assume that V prime approaches to 0 because the rotation of the element is very small. As a result, V prime power by 2 will be very close to 0, and then this is almost second derivative of V. Now, if we substitute kappa in pi function, pi function will be 1 over 2 0 to L EI second derivative of V power by 2 dx minus P over 2 0 to L V prime square dx. To solve this, as far as we do not have V, then it is easier if we use the variation method. A small variation is applied. It looks like derivatives, but with different definition. So delta I will be 1 over 2 integration 0 to L EI. Now we need to make the derivatives of the variable, which is second derivative of V power by 2. So it will be 2 second derivative of V by respect of delta second derivative of V dx minus P over 2 0 to L for V prime, it will be 2 V prime delta V prime dx. We need to continue and solve this parametrically, so it cannot be done with, for example, MATCAT, since there is no numerical solution, or not algebraic. I cross 2 and 2, 2 and 2, and let's start with integration of e by second derivative of v delta second derivative of v times dx from 0 to L. If you remember from integration basics, integration of u dv can be written as u times v minus integration v du. Just as reminder, I'm quite sure that you had it in the former courses, mathematics basics, mathematics, or other relevant courses. Now here I assume that ei second derivative of v is u and delta second derivative of v is dv. As a result, du will be ei second derivative of v prime. So dv is delta second derivative of v by one step integration. V will be delta v prime. Now I can substitute these in equation number 1. So the integration, the first integration will be u times v, which is ei second derivative of v delta v prime minus integration of v du, vi second derivative of v prime times delta v prime dx. You might ask, okay, when we can stop? We can stop when we have delta v in integration. Again, we continue the same method. This time, this is u and this is dv. So du will be ei second derivative of v second derivative, and then v will be delta v. I will write this as number 2, equation number 2. And I substitute. Number 2 will be u times v, which will be ei second derivative of v prime times delta v minus integration of v du, ei second derivative of v totally second derivative times delta v dx. And now I can apply the same method to the next part of our equation. Let's call that part number 3. So number 3, the equation is t integration from 0 to L v prime delta v prime dx. The same concept. So this will be u, this will be dv, du will be v prime prime, and v will be delta v. So number 3 will be u times v, v prime delta v minus integration v du, v prime prime delta v dx from 0 to L. Now we have the first term and the second term of the variation of pi. So variation of pi will be ei second derivative of v delta v prime minus ei second derivative of v prime delta v plus integration from 0 to L ei second derivative of v second derivative delta v dx. This is for the first part or first term of the integration. Minus v prime delta v plus integration v p v prime prime delta v dx from 0 to L. Those parts that we already have the integration can be determined according to the boundaries from 0 to L, from 0 to L, from 0 to L. And the rest can be calculated based on their integration. So delta pi from here will be, I will just put them in different parentheses to make it easier. So it will be ei second derivative of v delta v prime from 0 to L, this is only 1, minus from 0 to L ei second derivative of v prime plus p v prime times delta v, and then plus integration from 0 to L, they are the same delta v and dx, so I can put them together, plus v prime prime delta v dx. And if you remember, when we make the derivative, we need to force the variation of total potential energy to be 0. So here we will have ei second derivative of v at L delta v prime at L minus ei second derivative of v at 0 times delta v prime at 0 for the first part, minus ei second derivative prime at L plus v pv prime at L delta v at L minus ei second derivative of v prime at 0 plus pv prime at 0 delta v at 0. And then plus integration ei the fourth derivative of v plus p v second derivative delta v dx. Now we have to come back to our case to check what kind of situation do we have for the beam. Let's start with a simple one. A beam with the length of L from point A to B, which is subjected to a compressive load P at point B. So in this case, we know that bending moment at both ends is 0, and also deflection at both ends is 0. Before that, it is good if we remember that ei second derivative of v is minus m, and ei second derivative of v prime is minus q, shear force and bending moment. Now if we come back to total potential energy variation, we will have minus m, let's write down, this is equation I. From equation I, so it will be minus m at L delta v prime at L plus m at 0 delta v prime at 0 minus minus q at L plus p v prime at L delta v at L minus q at 0 plus pv prime at 0 times delta v at 0 plus integration of ei, fourth derivative of v plus p, second derivative of v delta v dx. So please note that the first term ml m0 are representing only the beginning and the end of the element. The second part also is representing from the beginning and the end of the element. And the last part is the only part that is representing the entire length of the element. So from here, I know that the bending moment at both ends is 0. So ml is 0, m0 is 0. So then I can just cross these two. Also, I know that delta v at L is 0, delta v at 0 is also 0. Then I can cross the other part. And from the third part, to force it to be 0, the function of the integration should be 0. So ei, the fourth derivative of v plus pv zagon should be 0. The conditions relevant to deformation are called essential or kinematic boundary conditions. Boundary conditions related to the bending moment shear force are called neutral boundary conditions. And the last one, which is representing the entire length of the beam, is representing the equilibrium boundary condition. So it means that in the entire length of the beam, we need to fulfill this equation. It might be a little bit weird that why we already knew these two equations or these two conditions for the bending moment and deformation. In this example, it might be hard to explain especially the neutral boundary conditions. Let's go through the other example. It might be a better example to explain for a cantilever one. Let's assume we have a cantilever column subjected to the force P. And the length of the element is L. So here, at x equals to 0, variation of v is 0. At x equals 0, also variation of v prime, there is no slope or rotation. So these two are called essential boundary conditions. So these two are essential boundary conditions. So if I apply delta v at 0 is 0, then this equation will vanish. If I apply delta v prime equals to 0, then this equation or this term will vanish. And then we know that delta v prime at L is not 0, delta v at L is not 0. So then it should be in a way that m at L should be 0, that we know already. And also q at L minus pv prime at L should be 0. So here you can see that the neutral boundary condition is not as same as what we assumed. So these are called neutral boundary conditions. And then the rest, which is the equation for the entire length of the beam, is called equilibrium boundary condition. If you are interested why we have shear force at the end of the beam, if you sketch the beam, and if the deformation is sketched, the force is here, and now to calculate the shear force, we need to apply the cut perpendicular to the deformation form. So here you can see that we have some shear force. It is not applied in the lateral loading or bending finite element method. This is just for buckling. Now, if we look at the equilibrium boundary condition, it is with the order of 4. So if you solve it, this differential equation, you will have 4 unknown parameters A, B, C, and D. And if we look at the essential boundary conditions, here we have 2 essential boundary conditions, and also we have 2 neutral boundary conditions. So we have 4 boundary conditions plus 4 parameters, unknown parameters that we have to find out. So whatever the beam is, you will have the same concept. So let's try something else, for example, just to understand how it works. X equals to 0, x equals to L. So here delta V at 0 is 0. So then this is gone. Delta V prime at 0 is 0. So delta V prime at 0 is 0. Delta V at L is 0. So the remaining is delta, I can go with another color. Delta V prime at L is not 0. As a result, ML needs to be 0. So again, you can see that we have equilibrium boundary condition will be EI, the fourth derivative of V plus V, second derivative of V, E times second derivative of V equals to 0. And then we have 4 unknown, we have 4 boundary conditions. The first 3 are 3 essential boundary conditions, and the last one is the neutral. Let's try another case. Assume that we have this type of beam, x equals 0, x equals to L, and I'm going to use the same method and apply the same equation. So here we know that delta V at 0 is 0. This is gone. Then delta V prime at 0 is 0. Then delta V prime at L is 0. And the final one, so delta V at L is not 0. As a result, minus QL plus PV prime at L should be 0. That's the way how we need to solve these type of equations or questions. So the first 3 are the essential, and the last one is the neutral boundary condition. Now, in this example, we are going to solve one cantilever from one side, and the other side is supported with horizontal support subjected to force P with the length of L and the bending rigidity of EI. And let's assume that the bottom of this column is x equals to 0. So we have the equilibrium equation, which is EI, the fourth derivative of V, plus P, second derivative of V equals 0. And delta V at 0 is 0. Delta V prime at 0 is 0. Delta V at L is 0. I can remove delta. And also, we know that M at L equals to 0, or EI second derivative of V at L equals to 0. First, we need to solve the fourth degree differential equation. It will be fourth derivative of V plus P over EI second derivative equals to 0. I assume P over EI is lambda powered by 2. So then it will be fourth derivative of V plus lambda 2 second derivative of V equals to 0. To solve this one, we substitute V fourth derivatives by R4 and second derivative by R2 to form the characteristic equation. So it will be R fourth plus lambda 2 R2 equals to 0. I factor R2, R2 plus lambda 2 equals to 0. So then I have 4 roots. R equals to 0, R equals to 0, R equals to plus minus lambda I. And then the homogeneous form of this solution will be, because of lambda, complex number, imaginary part, it will be A sinus lambda x plus B cosinus lambda x. And for 2 times having 0, it will be e powered by 0x times c x plus d. You can refer to basic differential equation solution. As a result, the form of the general form of the solution will be A sinus lambda x plus B cosinus lambda x plus Cx plus D. So it means that regardless of any boundary conditions, always we face this type of equation if there is not any action. Now we have to apply the boundary conditions. Let's find out the second derivative, A lambda cosinus lambda x minus B lambda sinus lambda x plus C, and the second derivative will be minus A lambda 2 sinus lambda x minus B lambda 2 cosinus lambda x. Now we can apply the boundary conditions. V at 0 is 0. So V at 0 is 0. I would advise do not solve them like a basic equation. Just write down the conditions. So V0 is 0. Then I can rewrite or Y at 0. Whether I change these to V. V. The last one also second derivative. So then B plus D will be 0. The second is V prime. At 0 is 0. A lambda plus C equals to 0. Then V at L is 0. So A sinus lambda L plus B cosinus lambda L plus CL plus D equals to 0. And then second derivative of V at L equals to 0, representing the neutral boundary condition. So it will be A lambda 2 sinus lambda L minus B lambda 2 cosinus lambda L equals to 0. Here you can see that again we have 4 equations, all of them are equal to 0, and then we have A, B, C, and D. To have non-trivial solution, we need to force the determinant of this coefficient matrix to become 0. For A, 0, for B, 1, for C, 0, for D, 1, then lambda 0, 1, 0, sinus lambda L, cosinus lambda L, L and 1, and we are not looking for lambda 2 equals to 0. I can just cross them, and also negative sign, so it will be sinus lambda L, cosinus lambda L, 0, 0. If this is matrix T, then determinant of matrix T should be 0. T is a function of L and lambda equals to matrix 4 and 4. So 0, 1, 0, 1, lambda 0, 1, 0, sinus lambda L, cosinus lambda L, L and 1, sinus, cosinus, 0 and 0. And now determinant of E as a function of L and lambda. So it will be minus sinus lambda L plus lambda L cosinus lambda L. And it should be 0. So lambda L cosinus lambda L minus sinus lambda L equals to 0. So it was lambda L cosinus lambda L minus sinus lambda L equals to 0. And from here, it will be lambda L equals to tangent lambda L. Or I can write down lambda L minus tangent lambda L equals to 0. Now the buckling modes can be calculated based on the minimum lambda that satisfy this equation. We can continue with this control copy. You can use the solver block, put it in constraint, equals to 0. And so let's assume lambda L is x. And the x value for the guess can be whatever 2. Then we can find x. Find x. So you can see that it is very close to 0. It means that this solution resulted in the very so x equals to 0 should be one solution. I can increase this value to check what would be the next one. here you can see that it goes to the negative side. So we can just increase it to, for example, 4 and then 4.93. There is another method that I usually use. It is very handy. I sketch the graph, for example, of the function. Then I will see where it will be the root. It is very handy with the plot. So here it can be function of y-axis and the other one is x. So I limit from 0. So here we can see that how it looks like. Usually it is not solved this way. If I increase the value to, let's say, 20. So here you can see how many times we have the solution. This might not be very interesting for many researchers. It might be better if we go with the other equation that we found, x minus tangent x, because then you can see the period of the solution. So you can try it. The first one is somewhere about 4.493. So I can write it down. Lambda L1 will be 4.493. If you are interested in the second mode, so it's very close to 8, I can change this value, the guess value, to 8. It is 7.725. And so on. And from the first one, I can find out what is the buckling load. So lambda 2L2 will be 4.493 powered by 2. 4.493 powered by 2, which is 20.187. And then lambda 2 represents P critical, the first one, divided by EI times L2 is 20.187. And from here, we can find out P critical one is 2187 EI over L2. If you want to write down in a way to find out what is the buckling length, P critical 1 will be pi 2 times EI divided by L power by 2, 2187 divided by pi 2, and then it can be written as pi 2 EI divided by L2 times pi 2 divided by 2187. So it will be pi 2 EI over 0.49 L2, or I can write it down pi 2 EI divided by 0.7 L powered by 2. And you can see that we got the same answer. L effective or critical length for the buckling is 0.7 L. The same value in Euler calculation. If you are interested in higher orders of the buckling loads, you can find it by the next root of the equation. Yes, that was the end of this example, and we went through the essential boundary condition, or it is also called kinematic boundary conditions. Also, we went through the neutral boundary conditions. I provided some examples, and at the end, we applied one of these to the one case, and we found what is the buckling load. So this is how we can derive the buckling load from the total potential energy in a beam. I hope you learned it, and see you in next videos. Thank you and bye.